Okay, good morning, let's get started. It's a great pleasure to have Professor Tardos of Cornell talking about learning games.
Thank you. Thank you for showing up so early. So I'm going to talk about, I guess, learning in games, but the main focus will be in a game that's not stable enough, and I guess that's what dynamic population stands for. That is the population exchanging underneath. And I guess for connection to the theme of this year and the theme of the workshop, if you participate in such a game, you're going to have to observe that something changed and learn from it. So at least the information feedback model I'm thinking of, learning will become necessary feature that people have to do as they participate. So I guess maybe the prime game I want to think about is traffic routing. Similar things apply to online advertising for the very same reason. Online advertising is yet another thing where you participate over and over again. Here in the traffic routing case, I guess maybe best to think of the routers as the players, and the routers certainly are routing packets over and over again as time goes. For this talk, and that's actually not necessary for the results, and maybe I can say a little bit more about how general the results are. I'm going to focus on congestion games. So a congestion game is one where the cost depends on how many other people are using the same edge or same node or same path, or how much the congestion is on a particular link. But again, the focus is that traffic streams are changing as time goes on. So there will be game repeats, but sometimes the certain traffic streams or certain, you're downloading some data from a website and you're done reading the New York Times in the morning. Now you're no longer downloading that one. You either switch to something else, or someone else is downloading something else, or whatever else is happening. Something that may be not explicitly written on this slide, but will be necessary for anything I can tell you, is that the speed at which these changes are happening, of course, is a bit slower, or quite a bit slower than the speed at which repeats occur. If every single second there's a whole different set of things going on, then learning is maybe not the right attitude here. But given that my assumption is that the learning, that you stay in the system somewhat long enough so you have a chance of figuring out what's going on. So a repeated game will be a very simple model, discretized time. Every iteration, people take some action and something happens, and then next iteration and something else happens there. I'm going to assume that the objective function of the player is average delay or average performance, so summing up performance over time. In the case of packets, I guess maybe a slightly better objective, which maybe one can adopt some of these things to, allowing packets to get dropped. But average delay is at least a standard summarizing objective function here. And I guess the main assumption, and I guess the main connection for the theme that we have been pursuing here this workshop and this semester, is that I'm assuming the players want to take the input from the previous runs and what they experienced in the first few times, and want to learn from that data. I guess there's two reasonable questions that I guess one should ask. What can one say about the outcome that is maybe better phrased? If the people stay long enough in the system, then they have a chance to learn. And then hopefully I can say positive things about that this sort of learning without any central coordination will lead to reasonable social outcome. If they don't stay in the system long enough, this is kind of hopeless. So maybe one quantitative way of phrasing how stable has to be the system or how stable has to be one participant for the good things to start happening, just based on learning without central coordination. So there's a large community, including me, who have been thinking about quality of outcomes in selfish situation, and maybe my old result is one of my favorites for sure, is trying to compare Nash equilibrium with a socially designed optimum, and maybe one classical result of this form is about traffic routing. It says that a cost of a Nash equilibrium, cost here is complete total delay, is no worse than the cost of optimally routing twice the delay. I guess this is sort of where I'm coming from as a basic result, but please note that this is a one-shot game with a one-shot Nash equilibrium, and what I want to do is repeat the game, and actually not the same game, or more precisely, yes, the same game, but not the same participants. So, but the notion that I'm borrowing here is this price of energy, which is how I'm going to measure how good the outcome is, cost of Nash equilibrium divided by cost of the optimum. So if you're within 30% up from the optimum, as a theoretician, I'm going to view that as reasonably good, compared to if for n players you factor n off from the optimum, that's going to be viewed as horrendously bad. I hope you agree on the horrendously bad, and I hope you agree that compared to that, the good thing is reasonably good. There have been a beautiful set of literature by many other people, I guess, on traffic routing style games, and actually the kind of games I'm not talking about today, but the results also apply to lots and lots of auction games. So different auction setups, they all prove in this price of energy bands in the small constants, some of them 2, which I still view as a somewhat small constant. I'll come back at the end of how one can try to make these things better, but that's not the focus of my talk today. My talk today, actually, the focus of lifting this to this sort of dynamic repeated game. So what's a dynamic repeated game? And this is mostly based on, I guess in the beginning I listed a bunch of co-authors whose work it's based on, but large part is based on Tardos, Lykouris, and Syrgkanis, whose pictures you can see up there, and I'll have pictures of the others as the results come up. So the model we want to use is we play one game, and to make it concrete, let's think about traffic routing game. But if you prefer auctions, then it's an auction game where people are bidding in the auctions. Every iteration, each player has some small probability p at which he decides that he's done. I'm going to keep this is a randomized event, that is, take probabilities here. But then he's going to be, if he vanishes, he gets replaced by a worst case other guy. Now, what does it mean that he gets replaced by a worst case other guy? One hand, even if I keep this probability very, very small, like 1 over the size of the population. So for n players, 1 in n, that means every iteration something did change. Or in general, if it's probability p, then with n players, p times n players get replaced. So in expectation, something changes. To give away the punchline, I will be able to keep this probability pretty damn small, pretty damn, actually, big. The changeover pretty big. But something of the not quite as, 1 in log n or something. But still, close to a constant fraction of the population gets replaced. So there is a significant change happening in the population every single iteration. Because it's, the population changes all the time, there's definitely a need to adjust. And I'm not feeding any information to them. In particular, notice that the replacement is worst case, and I'm feeding no information to them. So they're going to have to learn from their own experience in the game that, wait, some things appear to change. Like, I kept always driving on this road. There was no one here, but the last couple of days, it has been horrendous. I better try exploring something else. Yeah.
So you're assuming that the size of the population stays the same? You're just replacing it?
Yeah, that's an excellent question to ask. I admit I'm a little bit cheating here yes, I'm making the assumption that Asu made for, I think literally just for mathematical simplicity, that the size of the population stays n all the time. So if someone leaves, it gets replaced. We probably should improve it, extend it to the replacement is probabilistic also, except the properties of the new guy is worst case. Good questions, thank you. Okay, so first let me actually tell you a little bit about what happens in learning and what's known or what's standard in learning in repeated games. So the classic learning when you repeat a game is actually a really, really old question. And the maybe first or the first that I know of person who really started to think about it was Julia Robinson in '51, which I admit was a long time ago. The question she asked is one particular learning, and I guess this is her called fictitious play, which you simply pretend to believe that the opponents are randomly sampling from their distribution. They're not adjusting to the game, and you think of the play as random sample for their behavior and best respond to that one. That's called fictitious play, and that's what Julia Robinson studied. And I guess maybe not as much want to focus on her results, though I have it on the next slide, but the question she asked, she was thinking of this as a pre-play, as a way to find the Nash equilibrium. And that prevailed for a long time in history. In fact, there are two of these beautiful results out there. Julia Robinson's result that on two-person zero-sum games, it actually does happen, that two-person zero-sum games, fictitious play does converge to Nash equilibrium, and extended result on an even sort of more specialized version, two-person, not zero-sum, but 2 by 2. We all have two strategies. That too has the property, but this is about it. After this does not converge to the Nash equilibrium. Pre-play is a reasonable thing to do if you're playing a game sort of like the incentive auction, that is the spectrum auction that just happened in the US, where there was one really important, one big event in life, and they did actually do pretend plays of this form to try to have the participants learn how to bid in it. And then there was the real auction. This is the framework she was thinking about. I'm, in contrast, thinking about a framework where auctions happen all the time. There isn't one big auction, but auctions happen all the time, like ad auction or like traffic routing. It's not like we think about it for a day and then in the evening we route all the packets. Instead, we're routing them all the time. And there's no distinction between the real and the learning, but instead of wanting them or expecting them to converge to Nash equilibrium, I just hope that they learn something and hopefully they're better off when they learned. So I guess the notion of learning that's very helpful here, or what I will use, is something called no-regret learning, which I guess from a it's very Nash equilibrium-like, without the assumption that they reach some sort of Nash equilibrium, and this is what Nash equilibrium would like. So the assumption would be that they somehow vary their cost. They do at least as well as a single thing with hindsight, or at least not much worse. If they do a little bit worse, that's called regret. Two defenses for this notion, which maybe all of you are very familiar with, so I'm not going to spend a lot of time on. So what this means in plain English, that if there's a really good solution X, sooner or later they wake up to it. How much later is the error? That they're very simple and natural algorithms that can push the error down to roughly root t, which is usually called no-regret algorithms, where no-regret here means regret going growing less fast than the time, or going to zero relatively. It's also known that if you repeat the very same game, then no-regret learning will converge to something called correlated equilibrium, and maybe the notion of correlated equilibrium will make you feel more the connection to Nash equilibrium. It's a distribution. So Nash equilibrium is a distribution where different players independently choose actions, and then something happens. Correlated equilibrium is literally the same thing. I just took out the word independently. That is a distribution where we correlatedly from a joint distribution pull actions, and the very same rule applies. No one wants to deviate to a different action. So long-term play converges to correlated equilibrium, and just to get you a sense if you didn't, of course it's the past history that we're correlating on. We can correlate not because there's a correlation device, but instead because we're all learning from the very same history. So that's sort of in a single game, learning in a single game fashion. Before I move to what I really want to talk about is this dynamically changing population. I want to actually slightly change what I mean by this no regret. I want to change to a bit more permissive version of no regret. And I guess this was suggested by a recent paper of ours with Dylan Foster, Kartik Sridhara, and also Tardos Lykouris. Oops. Sorry, these two pictures should be backwards. This meant to be alphabetized, and I messed up. Alphabetic order sitting here, sorry. Which is a bit more permissive version of no regret learning, where I allow you a multiplicative 1 plus epsilon error. That is, if you're going to take an hour driving to work, then let me assume that 5 minutes plus and minus is not going to be what you're optimizing on, that there is an error, a fixed error. Think of it, say 5%, 10%, that this is the error that you're willing to tolerate. The reason I really like this version, two reasons I really like this version. First of all, the additive, once I give you a percentage multiplicative error, the additive regret error goes really, really small. That is, the dependence of time goes away. That's just the number of options, or the size dimension of the option space is what matters, and the time doesn't matter anymore. It's a constant learning error. After that, you can keep up with this error. And the second reason I like it, because having looked at auction data, this seems to pretty well match of what people are doing. This actual no regret doesn't. They don't appear to, humans, automats, learning algorithms don't appear to optimize to the last percentage. This is like with actually a pretty big epsilon, like 5 or 10%, matches data reasonably well. If you go push the epsilon lower, it starts matching it less and less well. Yeah.
So if instead of total or average cost, we think about the discounted cost, would that somehow match this regret notion better? Because there's a delta to the t in front.
Would it match better?
Or maybe
I guess I haven't thought about, maybe we should talk about this offline a bit. It would extend to that notion. I always thought that there is a, historically, no regret algorithms, people think of the error as an additive error. And actually, if you go back to your very first algorithm of this kind you ever heard, this is how it starts, and then they choose the epsilon to optimize this expression. And I guess looking at data, it does seem, and I admit that's auction data, it does seem like that's not happening. People are picking a fixed epsilon and they're not optimizing the epsilon because at the end they don't care about the percentage. And I think that's really not like, this is a sort of an attitude difference. How well do you care to tune your learning rate well enough, or seems like people don't care and not as much a difference between the discounting? Like do you really do the utter optimization to adjust to the data or in your learning rate, or you not do that? I guess here is a bunch of data sets that I did look at where the suggestion came from that this is maybe a good notion. And I guess, interestingly, if you look at the set of papers here, so this is the data set I looked at. That's Microsoft advertisement auction. The rest of them are all actually human subject experiments. And interestingly, two of them, the Nissan Noti and the Fudenberg paper, actually making upfront the opposite point, saying that the agents aren't learning. But if you look at the data, then learning actually matches the approximate no-regret learning matches the data pretty well. Actually, the most interesting paper from Asul's question is the Fidenberg paper up here, where their main conclusion is people are very heavily recency biased, which, of course, if you do learning with a discount, then this is the right learning. So I'm happy to come back and maybe offline too. But this is somehow the most relevant paper to your question, because they're doing a. They're claiming that discounting matches better the behavior than learning. Okay, so again, what I said is price of energy was originally introduced by Koutsoupis and Papadimitriou, and I said the cost of an ash versus the cost of the optimum. Actually, there have been a beautiful sequence of papers taking no-regret learning in a fixed game. I don't know if that, like very identical players, identical game, which extends the price of energy notion to learning outcomes. Here is what they do. They say the cost of Nash equilibrium, there were capital T iteration, the sum over the T iteration. It's a fixed game, so the optimum never changes. So divided by T times the optimum, that's the average ratio. And they take those results and extend it to this sort of learning outcome. I think this stream of papers was originally started by this Avrim Blum and company paper in 2008. There's a couple precursors, and then there's a very general, beautiful framework by Tim Ravgarden, which I'll come back to in a second. And what I want to talk about is extending this to where I'm allowing the population to change too. So what I have in mind, instead of my price of energy, is the same cost as cost goes to cost of over time, but instead now the optimum is changing also, so I divide by the sum of the optimums as they happened. I think this is a reasonable objective function. I hope you accept it. Clearly, I can't possibly hope, given my data feedback model, that every single one of these ratios without the sum stays low. If something changes in a population, it will take the players a couple iterations to wake up to this fact. So all I'm claiming, on average, they're doing okay. Yeah?
By optimum, do you mean societal optimum or per player optimum?
So societal optimum. In a game, it's not clear to me what the player optimum is.
So represents optimal utility of this player.
It's a societal optimum. Optimum over social welfare, sum of all the players. Average delay of all, like, I guess what's in the delay is average delay of all the players as it happened, and average delay of all the players had we tried to optimize that quantity.
So there's no averaging over players going on in any of those?
The sum of the players. The social cost is the sum of all the costs. I'm not averaging any place as summing, but that's mathematically equivalent. Does that make sense? I guess this is actually part of the places where my cheat came in, that I kept the population fixed. Because otherwise I should keep averaging, and then I'm dividing everyone's experience with a different number depending on the population size. It definitely is very convenient that I have the same population. I don't have to worry about that. Okay, so that's the model. That's the version I want to think about. And to tell you what maybe how I want to think about, or what I want to tell you about, I have to go back to this Tim paper and tell you a little bit of how these price of energy bands were proven. Actually, for this talk, maybe only keeping sort of one major message, which I think, at least for our purposes, is the major message here. What Tim did in developing this framework that says that price of energy results extends to learning outcomes in a fixed game is to observe that almost all, or virtually all, price of energy results go on a very, very simple framework, which he called Smoothness framework, and this is what they do. He says, okay, there is one thing we know about the Nash equilibrium, and that's this inequality here. If A is a Nash equilibrium, the thing I want to think about, why doesn't the player do what the socially designed optimum wants him to do? Why the hell isn't he switching to what I, as designer, know is optimum? Let's call that AI star. That's what the optimum would be. And I know he's not switching because apparently it's not good for him. That's this inequality. So he currently has cost I, and this would be the cost if he switched, and apparently he's better off. And this is, in a very simple proof, this is all I want to be able to use, this one inequality. And he says that apparently many games, our proof comes down to an inequality of this form, which I'll come interpret in a second, taking this sum of the player costs in this funny deviating, everyone single-handedly deviating to the optimum, and comparing it to the optimum. Now, when I first taught this in a class, I actually started the price of energy segment of my class with this, and I got the advice from the students that, well, yeah, of course, you made up some inequality just exactly so that you can prove the price of energy. And indeed, it's almost designed like that. Once you have this, you add the inequality you had. That's the cost of sum of the cost of players. What you got here is the cost of the strategy A, and you just rearrange and get the price of energy band. And this is precisely how all the proofs go. So my students were right. This is precisely designed for the right thing. My point is, almost all the proofs follow this framework. This is how the proofs go. To help you interpret this in case you haven't been as used to it as I have, I guess what this inequality really says that if the cost of your current solution is extremely high compared to the optimum, if in this inequality, despite mu being below 1 and lambda being above 1, this is the dominant term because the cost is super mooper high, then apparently someone can improve. On average, they can improve. Someone can improve. Clearly, that means it's not Nash. Someone will want to deviate to our side. The beauty of this inequality is that this automatically lifts to learning outcome in a fixed game. And here is how. In a learning game, again, going to my approximate version, we get some sort of inequality, not about an individually, that individually they like what they did better, but at least compared to this optimum, and remember, go back, only inequality I cared about, how they care about the optimum. So they don't regret not switching to that fixed thing called the optimum. Again, combining with the inequality, you get something by rearranging the terms. One maybe interesting thing to notice here, other than the epsilon showed up because I put up an epsilon, is the form of this regret, the term coming from the regret error, and I guess that's the point of one of the points, or one of the interesting points of switching to this epsilon version is that the speed at which they're converging to this outcome is now very fast. That they, rather than a 1 over root t kind of speed at convergence, they have a 1 over t style convergence. So they're converging to this socially good outcome in a super fast way, which is going to be handy once I start changing the population. Okay, so this is all about the fixed game. Remember, we want to mainly focus on non-fixed games, that is games when the population is changing as we go. And again, what I want to assume is they're learning from data. Now, I have to actually start thinking about what do I mean by learning from data. So again, remember driving, or remember a router gets ping, gets feedback that no, that packet never went through, or that took forever to go through. How do you learn from data? Our no-regret notion said this, and again, I like the epsilon. So your cost over time is no worse than, low bit worse than a single fixed coin with hindsight. Now you can think about this as, that was in our proof, what we have in mind, this will be the optimal solution. And with changing populations, there is no such thing as the optimal solution. Or you can think about it, this is really not a good idea. The whole point of learning is that you should learn to adjust to the situation. And learning is better than Nash equilibrium precisely because you will react to what's happening in the world. This is not expressing that fact. It says that, if there's a fixed good thing, you notice it. So I want to actually change the notion of learning a little bit, and maybe that's the moment I'm coming back to Asu's question. Instead of no regret learning, which I need, so just to drive home the point that you need this, fixed strategy with hindsight is very weak. So here is a repeated game. This red guy is the person I'm thinking of. When he shows up, it turns out there's a lot of traffic in this upper pass. He chooses the lower pass, and he, whatever, he's happy. And then, for whatever reason, those guys vanish, and so those packets vanish. But instead, these guys show up, and he says, well, I'm having a bad experience here. Lots of congestion. I need to switch. He needs to adopt. This is exactly what we wanted to model, that players do adopt to the population. Okay, so this is from the literally it's necessary perspective. Here is the proof perspective. I showed you the proof of how we proved this price of energy bands. So what would I need to adopt my proof to the price of energy band? I would need something like this. I would need a proof of this, that the cost that they're experiencing compares well to the optimum cost. And if I had this, I would be home, same proof. And what is this? The only thing changed that the optimum is now a fragile object. It's indexed also by the iteration count. Of course, maybe you will realize that this is just no way. It's not even hopeful to adjust to this. How can you possibly learn if I'm changing the optimum on you every single time? You had a question?
Should we think of A's as different bids options or different mappings between values and bids?
I was thinking of different bid options. And I guess I'm really thinking of traffic routing. So a player does not change his source-destination pair during the game. You still live where you live and you work where you work. And if you change your workplace, that's actually a change event. Like now you're not the same person or not the same traffic pattern. For an auction version, I guess you can think of it as a different mapping. And again, A star is not necessarily optimal for you. That's optimal for social welfare. There's not clear you want to do this. The social designer wants you to do this because it's good for social welfare. This is what I would want, but this is really not hopeful that people can learn this well. And maybe naturally, of course, unfortunately, one thing you would hope is that this isn't such a fragile object, this optimum here, but the optimum is actually a very fragile object. So maybe in this audience that doesn't need to be driven home, but even if I run a sort of matching game and have a matching optimum, one guy leaves, and the matching changes on literally everyone. We change on a ginormous segmenting pass. So that, the optimum itself is a very fragile object. So let's start from the other side. How well can I learn? And I guess going back to this epsilon regret paper, we actually did work out for the same reason of working in part on this project. How well can you learn? And this is something that actually very same algorithms almost take care of. A little bit the way Asu wanted me to do it. A little bit discounting, actually this time discounting the past. That is putting in a bit of recency bias. So taking the very standard learning algorithms and hitting them with a slight recency bias, with a discounting the past with a 1 plus epsilon, 1 plus delta rate. And this is the kind of things they do. It says that if you want to learn, instead of a fixed x with hindsight, you want to learn well enough for a changing x with hindsight. Of course, the more x changes, the more hopeless it gets. But if x will only change k times, I guess your regret error will, in our case, will go linearly with k. That is, in a fixed epsilon, epsilon over k is the way I'm multiplying the regret error. That is, but some of interesting facts about is, I don't need to know how often it will change. Of course, I'm not getting warned that that system changed. So if you were think of this as, I will warn you every time the system changes, this isn't surprising, right? Because with k changes, the system consists of k phases, each of which you get this error. But the point is that I'm capable, or we can do this, or the same algorithms take care of this, even if you're not warned when the change happened, and you don't even know how many there will be. So your algorithm runs in a fixed epsilon. It cannot adjust to the number of changes because you don't know. Very natural algorithms take care of this sort of changing error. So as long as I can keep the changes low, people will learn well enough compared to that in a no-regret learning algorithm. So at the very high level, this is where we get to sort of at the theme of what I did without the mathematical details. If the game is part of this price of anarchy that's proven with the smoothness property, so the game has the smoothness property, and I were to be able to generate a close to optimal, not really truly optimal, but close to optimal solution that's very stable, doesn't change very often, and the people do this recency biased learning, then I can keep the price of anarchy in this, even in this changing environment, close to the price of anarchy of the optimal solution. And I guess just to remind you that instead of giving you the details of the theorems, which is coming in a second, I gave you the outline of the proof. What the proof did, instead of using the true optimum, I use the stable approximate optimum in my proof system. I assume that they're doing some no-regret, recency bias, no-regret learning of the kind that generates this epsilon over k over epsilon sort of regret error. If they do that, then the same price of anarchy proof will adjust. Making it a bit more concrete, here is a sort of summary of the nicest things we can say. And again, this is, I guess, works on traffic routing games and a number of different games. So if I have a price of anarchy proof for a game that's along the smoothness framework outline, which is almost all of them, then I can keep a roughly 1 in log n population size change. The log came from the regret error. Remember, there was the log d regret error, which I have to make go away. So I have to keep people in long enough that their cost dominates the error, that the error is not the main part here. And the no-regret learners, then I guess a price of anarchy we can prove comes in 3 different parameters. And if I take a generous view of what the game is, then all parameters can be made to go to 1. So the product of 3 different things. Alpha is the price of anarchy. And I just copied the price of anarchy proofs. Not because of our results, but because of some other work by Vasily and some of his co-authors that I think is nice to quote here. If you make the game larger and larger in population, they have beautiful results that says the price of anarchy goes to 1. That is, if you're doing a routing game, the more people are around, the less price of anarchy you have, which is a nice observation to make. There is a separate thing I called gamma, which is the regret error. I optimized with the 1 over p1 over log n. I just went to the edge when the regret error doesn't dominate the loss. Then, of course, I'm losing a factor of 2 because I have half error, half cost. If I'm willing to p go faster to 0 than that, then, of course, that error goes to 0 also. And a third part, which I maybe will spend 1 more slide at the end, is the loss to the optimum. I need not the true optimum, which might be very fragile, but instead I need a stable optimum, where the particular people's parts not changing as the game changes. And there also, we can show that as the changeover is going to 0, stability can go to 1. That is, the loss of, you can get the stable optimum without actually losing. And so let me spend 2 more slides at the end, is trying to talk about this last item, the stable optimum part. So what does it mean that the optimum is stable? So maybe the simplest thing is if you're really totally willing to change your optimization algorithm, you're not getting the true optimum. And that one is so simple, I think in 2 slides I can at least convince you that, yeah, there might be something in here. So if I change, this is a very simple example, again, back to matching. And remember, matching was very sensitive because you do a whole augmenting pass every time someone leaves. If I want a stable optimum, then here is something I could do. How about I change my optimization and do the greedy algorithm? The greedy algorithm, here I lost a factor of 2, so this is not going to 1. It's a literal loss of factor of 2. And before I do the greedy algorithm, I also do some rounding. Don't take those values so seriously. Do it within parse of 1 plus epsilon. Lost another 1 plus epsilon. If I do both of those, I claim it will get very stable. Now, what did I do here? I created tons and tons of ties in the greedy algorithm. And as literally the sequence comes on, I can resolve ties to keep stability in mind. That is, if you have an edge, I'll keep you. If there are other people tying with you, whatever, you have priority. That keeps it much, much, much more stable, enough stable to get all of our results. For a higher version, higher level version, and where the converging to 1 comes from, is a different notion of differential privacy, which is really the last thing I want to tell you. Maybe many of you heard about differential privacy in a very, very different context. Differential privacy, as the name suggests, is something about privacy, was championed by Dwork et al., but the particular notion on games I'm using is a Kearns paper, which is much more recent. It says that we're doing some sort of game like traffic ratting, and you want it to be that the central ratter will rat you in a way that gives you no information about who else is in the game. It wants to keep your information, give you a solution, of course you know your solution, but your information is private in front of everyone else. What does private mean in English? Really, it doesn't matter to them whether you're there or not. That's precisely what I also wanted. Our notion of stability is very, very almost identical to their notion of privacy. And in fact, one advantage I have over them, that if I take many of these papers, they usually struggle like crazy to make these things algorithmic. That is, they can prove that such a private solution exists, but of course, if a designer wants to hand you those paths, you have to make it algorithmic. I don't need this. This notion is in my proof. It's not in an algorithm. I don't care whether it's algorithmic. As long as it exists, I'm OK. So I'm a little bit better off than they are, but I guess it's a very simple general result, I guess, because I kept the general thing so, the theorem statement so abstract. Maybe I end with a particular definition. This is a matching version. And I guess in the matching using the greedy algorithm, we get a factor of 4 or 4 times 4 plus epsilon loss compared to the optimum. And we get that at a very high turnover rate. And I'm going to stop here, and thank you for your attention. And hopefully, some of the things, like I guess the one message I want you to take away is this, maybe the top line here on this slide. We have been, or I and a number of us thinking of Price of Energy have been talking about learning in games, and the game theory community have been doing it since the 50s, so even longer than we were. But somehow, the fact that learning is good because it can adjust to data, and learning in games as an outcome, they were somehow not connected as a single thought. And clearly, learning is good because it can adjust to data. And we should think about what does it mean in a game that learning has this property and how to take advantage of this. And I'm going to stop here. Thank you. I don't know. OK, Sid.
About the last part, so since you were talking about stability, so suppose you had a principal who could give you extra information about the setting. Does it carry over to saying that your solution just needs to be stable with respect to the information that everyone got? So let's say someone's giving you information, so many people are driving on certain days, and everyone is adjusting their solution to that.
What you're suggesting is that I can change my stability notion, I guess maybe kind of the way Arthur was suggesting, as a function of the input you got. Maybe, it seems like it. I need to think through. Like if I think of a strategy as a function of your outside input, then I guess everything will just carry over. You're right. It's a good point. I do have to, like, one awkward thing that does, and one needs to think through of what might be a good application here, is that in a traffic routing, I do know what the dimension of the space is. Like in a, it's a number of edges, because that's the dimension. Like you have exponentially many paths, but the dimension of your selection space is the number of edges. If I think of my strategy space as a function from advice or whatever, announced something, to my choice, that lifts the dimension of the strategy space, and that log D error suddenly might be actually a big error. I need to think through what exactly happened there. I don't have to keep the strategy space low, but I do have to keep the dimension of the strategy space low, otherwise exploration takes a long time. Yes, you had a question?
So in your definition of smoothness, or I think the definition has been defined earlier, if I replace the players with bounded rational players who want to converge to epsilon Nash and not the true Nash, I think as long as the smoothness condition is satisfied, we can still compute the price of anarchy without any change in anything else.
I mean, I did actually, so good point. So yes, originally it was defined by true no-regret learners with no epsilon, and you can just adopt the epsilon, and some extra epsilons show up. And I did have this on my slide. I don't know if I'm fast enough to page back. When I adopted to learning, I automatically put the epsilons in. So you're losing a little bit. So the band was lambda over 1 minus mu. Actually, the only dangerous part is that the mu gets multiplied by the 1 minus epsilon. You have to make sure that didn't go to 0. So epsilon has to be small enough that it doesn't wipe out that part. But yes. Okay, I suspect it's break. Thank you. Oh, well.
Did you have any lower bounds for your regret bound, whether there's like k changes? Is that something that's possible in this framework where you've got this kind of limit?
Yeah, this is, so there are two versions here. If I want to keep my version with the epsilon, then yes, because, and I kind of, very simple argument, even if I tell you where the changes occur, there is already a known lower bound on the log D over epsilon. And even if I tell you that now everything's changed, this is the moment, please adopt. K times epsilon, this is all you can hope. One interesting thing that we cannot do, and I don't have a lower bound proving that I cannot do it, in the different regime when people picking the best epsilon, if I were to know what K is, I can optimize this and pick the best epsilon, and it ends up with a root K kind of error. I don't know how to do that without knowing K, because you're not observing K. You don't actually know whether it's the cost high or is it that K was big. So, but I don't have a lower bound that I can't somehow drop my epsilon in a better way to get to the, so the open question here is, can I get down to the root K error, where this classical way of getting down the error to root K would be to take this formula and optimize for epsilon, which I can't do because I don't know what K is. That's open. But with the epsilon version, it's tight.
Okay, let's send the speaker again. We'll restart at 10:45.